So last time we talked about, we started talking about currents, current going through a wire, and we looked at some particulars, some things like the specifics of where current comes from and what is current. So I'm going to do a little bit of review on that, but I'm hoping today that we will we will go a little bit further and talk about Ohm's law. So last time we looked at the macroscopic, what's going on inside the wire, what are these electrons experiencing, and how does that give rise to current. And then today we're going to kind of zoom out here and look at what how's current related to voltage and related to something we call resistance. Okay, so that's where we're headed for today. So let's go back. Let me draw a little picture here. So we looked at a wire, and we said that inside a wire, in this wire, we have an electric field set up. So I think I had a picture like this last time. So you have some voltage here. I'll put, I don't know, some voltage. And then over here, you have a zero voltage. I'm just doing this as an example. You don't necessarily have to have a zero voltage, but just for our example. So that voltage creates an electric field. So we have an electric field on the inside of this wire. Okay, and that electric field gives us a force on these charges. So we're going to have electrons here. Let me just bring up my chat here so I can see you guys. Yeah. So we're going to have let me put a electron. So that electron is going to feel a force going this way. And that's what starts to move these electrons inside this wire, right? The electric field that gets set up gives a force, and then we start to have electrons moving. So we looked at that last time. We looked at a couple things here. So one of the things we looked at was drift velocity. Oh, 1 second. Okay, so we looked at drift velocity. Okay, which was, it's actually a pretty small number. And we calculated drift velocity to be related to, remember E is the charge of an electron, the 1.60 times 10 to the negative 19, times tau. Tau is a time between collisions, right? So this electron is bouncing around, and I think I showed you guys a picture with this. Okay, so I showed you this picture here. So this electron is bouncing around in there, and as it bounces around, it's colliding with these atomic sites. So the tau that I mentioned earlier, that tau is the average time, I should say. It's the average time between these collisions. Okay, so that's what tau is there, over the mass of that charge, in this case the electron, and then times electric field. Okay, so that's what we calculate our drift velocity to be, right? It depends on all these things. Obviously, the stronger the electric field, the larger drift velocity becomes. Okay, but then you have to worry about tau, right? That time between collisions, and that's really dependent upon the material, right? Different materials have different densities, different crystal structure is what we call it, and that's going to give rise to different time between collisions. Okay. So we calculated drift velocity, and then we calculated the currents, but in terms of all these things. So current, which is in units of amps. Okay, so let me define current here. We define current I as how much charge is flowing through your wire per second or over time. Okay, so that's how I define time. and we got a little bit, we got specific here. This value, or this equation, we got E, again, the charge, oh, come on. The charge of the electron, the 1.60 times 10 to the negative 19, right, is my fundamental unit of charge. So that's E times N. N is the electron, or the number density, electron number density. How many electrons do you have per unit volume? Times your drift velocity. Let me see here. There you go. Times your drift velocity times the cross-sectional area of the wire. Okay. Okay, so that kind of gives us an idea of current, right? If we have a large drift velocity, we're going to have a large current. If we have a large number density, right, more electrons available in the material, then we're going to have a larger current. And same thing with area. If you expand that wire, or it had a larger diameter for that wire, it's going to increase your area, which then increases your current. Okay, so current depends on all those things there. Okay, so that's the macroscopic, and so what I want to do today is kind of get away from the macroscopic. We know where current's coming from. We know where drift velocity comes from. Okay, so we're able to see what's going on as far as the charge goes. Let's zoom out now, and I want to start looking at the wire as a whole. Okay, so to start doing that, to start looking at this macroscopic, the big picture here, I'm going to look at something called not so much current, but current density. Okay, so current density is joules per, you know what, I don't know if I could do superscripts here. Let me see if the shortcut works. Nope. No. I guess I can't. No, that didn't work. Okay, well, I'll just do this. Okay, so joules per meter squared, right? It's not joules. What am I thinking? Amperes. That's right. So current density is amperes per meter squared, right? Current over area. Okay, so if I'm going to define current density like that, and so a couple things about current density. First, the symbol we use is J. So the symbol we use is J. And J is actually, when we're talking about current density, it is a vector. Okay, we are looking at a vector here. That current density is going to flow in the same direction as currents. So let me make a little note here about direction. Okay. So direction of current density goes in the same direction as current. And note, it's a little different. Current is defined as the flow. Okay, so we get a little bit into history here. Okay, so current is defined as a flow of positive charges, not positivity, positive charges. Okay, so why is it defined as a positive charges? Well, this goes back a little bit in history there. Before we talked about charges as electrons, and before we knew electrons were flowing through conductors, current was already discovered, and it was kind of hypothesized there that current was a flow of positive charges. So all of the industry and what's the word I'm looking for? All the standards went off from that. So all like circuit diagrams and everything like that, current stayed defined as a flow of positive charges. Later on, we found out, okay, it was actually electrons flowing through it, but for so long, current has already been defined as positive charges. So when we're looking at current, current's actually going to go the opposite direction of the electrons. And maybe I'll show you on my picture here. Okay, so in my little diagram up here, if I want to define current, I'll do that in green here. Current, you see the electrons, it's going to be moving to the left. Well, current is going to be going, oh, whoopsie. All right. Now, come on. Change that back. Oh, put that in blue. Okay, so current is going to be defined going this way. Okay, so kind of a weird thing that happens. When we're talking about currents, we're going to be looking at the flow of positive charges. So in my picture here, instead of going to the left, like the electron is moving, current's going to go to the right. Okay, so I meant to make that blue. I don't know why I changed it again. Okay. Oh well. Okay, so I'll keep that in green. Okay, so now that we have kind of that definition, hopefully it made sense. So current density is in the same direction as currents. And current density is defined as your current over A. Okay. So current divided by area, and if we look earlier, look at the bottom left side of your screen there. We define current, right? Current is ENVD or A, so this becomes E, the charge, the fundamental unit of charge, times N times VD. Okay. So that is current density. Okay, why is this important? What do we care about current density? Well, for a couple of reasons. Current density is going to come up later in something called Ampere's law. Okay, so we're going to need to know what current density is when we look at a very important law, particularly when it comes. I think was that chapter 31, I think. So Ampere's law becomes really important, and it uses current density. The other reason why we need current density is because if we explore this a little bit, we start to get current density in terms of something that depends on the material. So let me make a substitution here. Let me substitute in for VD. So VD, we said again, you can see on the left side of the screen there, is E tau over M E. Okay, that's my drift velocity, and of course I still have my E and my N. Okay, so I substitute in for drift velocity in my current density equation, and I simplify that. So if I simplify that and rearrange it, N E squared tau over M times E. Okay, so take a look at this in here. All that are all constants, right? So you have E, which is the charge of the electron, right? The fundamental unit of charge. That doesn't change. We have mass, which again is just the mass of the electron, so that doesn't change. We have N, which is a number density, so that depends on the material. And tau, the time between collisions, also depends on the material. So all these are constants and depends on the material here, so dependent on material. Put that there. Oops. Depends on material, like what material is used. Okay, so rather than looking at, N, tau, and knowing those values, because it's just all these are constants and just depend on material here, we could rewrite that as this. So I'm going to rewrite J and just kind of simplify this. And all those things there, I'm going to call sigma E. Forgot to put my vectors. Okay, where sigma is my conductivity. Okay, conductivity. Okay, and let me make this note. And so it pretty much just tells you how conductivity tells you how. Maybe I should define this. Tells you how easy it is for the electrons to move through the wire. Change that position there so you guys could read it. Okay, so that's conductivity. So the larger conductivity is, or the larger number you get there, tells you the more current density you're going to get, right? And ultimately the more current. Okay, so conductivity, a larger number means more current. Kind of the flip side of that is something called resistivity. Let's see, where can I fit that in there? Okay, so resistivity there. I'll make a little arrow to define that. And that's just the inverse of conductivity. And we're actually going to deal with resistivity a lot more. The units for conductivity, or sorry, units for resistivity, put that up here, is something called ohms. Oops. Ohms and then meter. Okay, that's my units for resistivity. Let's see. Whoops. Make that a little bit easier to read here. Oh, where's my, oh. Okay, so that's my resistivity there. Okay, so we went from, what did we just do right now? We went from the microscopic, right, with dealing with what's going on inside the wire, same thing here. We went from the microscopic down to macroscopic. So conductivity, you could find these values based on the material, right? You should look, there's tables we could look up, and we could find out what the conductivity is for gold, silver, copper, whatever conductor we're looking at. And we just take the inverse of that, and we find resistivity, right? What's that resistance that these electrons are feeling as they go through the wire? Okay, so kind of similar things, right? The inverse of each other. Conductivity tells you how easy it is to move through the wire. So a larger number here means you're going to get large currents. Resistivity, a larger number here means that you're going to get low currents, right? A high resistivity means that you have a lot of collisions. So the time between collisions is small. So you have a lot of collisions slowing down those charges as they move through the wire. Okay, so all we need to know then to find out this or this is just what material is being used, and that's it. Okay. All right. Do have a note on temperature dependence here. Let me see. Well, I'll come back to the answer here. Okay. So resistivity what we're talking about, that row that we looked at, does depend on temperature here. That the reason why it depends on temperature, let me see, I don't think I have a picture. All right, so here's a function. I'm not gonna, you guys don't have to write that down. I'm not gonna test you guys on it. Oh, come on. Okay, am I sharing this? What am I sharing? Let me share this so you actually see it. There you go. Okay, so resistance does depend on temperature, and there's your function for resistivity. Again, don't write this down. I just want you to know the idea behind this. But there is a function there in case you're interested. Where the reason why is because let's say you had an electron. Electron moving here with some speed, and there is an atom. Well, with higher temperatures, that atom starts to vibrate. Okay, it goes up and down, or left and right, it doesn't matter. But it starts to vibrate. And as that atom starts to vibrate, it increases the likelihood that this electron here, will collide with this atom. Okay, so with higher temperatures, you get more vibrations, and with more vibrations, you get more collisions. Okay, so of course, with more collisions means more resistance. Okay, so this is why it's dependent upon temperature. Yeah, so we're not gonna look at that, but I do want to show you something kind of interesting that happens here. All right, so there's a whole bunch of constants there. You can see resistivity. The numbers here, we're looking at is pretty small, right? 10 to the negative 8. So that's particularly true for conductors. So we want conductors, to be small resistivities. For insulators, right? Those resistivities go way up, which is what you would expect, right? Insulators are not supposed to allow charges to move freely through it. Conductors do. That's why you have such a huge difference between the conductors, right, an order of magnitude of 10 to the negative 8, and the insulators, right, which are a lot larger. Okay, so gives you an idea of what this resistivity is, or these values, and again, it's dependent upon temperature. We do see something interesting that happens. So let's go to the other side. If we increase temperature, we know resistivity goes up. What happens when temperature starts to go down? We start to cool that conductor. Okay, so resistivity does drop, it goes low, but then we see something happens. Resistivity drops down to 0. And when it goes down to 0, some really interesting physics happens. This is called, so there's this really popular graph there that you're lowering down the temperature, and then at some point, so we're lowering down the temperature here, and it's at some what we call a critical temperature. At some critical temperature, that resistivity drops, very sharp drop, and it does go down to 0, right? And even this 0 has been measured to very high precision, and it is pretty much 0, right? 0.0000. So at this critical temperature, it reaches that 0. You have that sharp drop off, and so with no resistance, current actually does move freely. No actual noticeable collisions here. Actually, this becomes a quantum mechanical effect. But the effect is you have 0 resistance, which leads, again, just at 0 resistance, I think you're not in a position, unless you studied physics before, to really understand the implications of that. With 0 resistance, you have no energy loss, and you're able to create magnetic fields pretty strongly. So there is this video here. Let's see. So this is called superconductivity. And a lot of research done in superconductivity trying to see what's the lowest temperature we could bring, or what's the highest temperature we could bring that to. Right now, that temperature is pretty low. Oh man, I forgot. There's someone a group in Germany, I think, brought that temperature up pretty high. By high, I mean like negative degrees Fahrenheit, but pretty high recently. I just don't remember the actual value. But anyway, it's a ongoing area of research trying to figure out what materials can we make so that we get superconductivity at high temperatures or at room temperature. Okay, so if you have time, there's this pretty cool video that that shows you why superconductivity is so interesting. We don't have time right now because I really do want to finish chapter 27 and maybe starting chapter 28 today. But maybe take a screenshot of this, or I guess you can see it when I post the videos. But pretty cool little demonstration of, and you know, decent explanation of what superconductivity is. Okay, so when you bring that resistance, or you bring those some materials to a low temperature, there is suddenly a sudden drop in resistivity, and now you get no resistance. Okay, so pretty interesting there. Okay, so that's my little spiel about the temperature dependence of resistivity there. Okay, let's go back. All right, so we have this conductivity or resistivity, as we've been calling it. So now let's look at the wire again. I'm going to redraw this wire here. Okay, this wire, let me redraw it actually. What am I showing right now? Yeah, you guys see the whiteboard. Okay, so let me draw my wire. Oh, get that out of the way. Okay, and so now I have a difference in voltage again. So I'll call this VA and VB. And we saw that current density is just I times A, or I over A. And we also saw that this could be related to the electric field, right? Either by conductivity or through resistivity. Right. So that's what we got from the previous slide, what current density is. Okay, so I'm going to use this and the fact that we have this change in voltage to start to see the relationship between current and voltage. Okay, and this is going to bring us to a really important law called Ohm's law. Okay, so let's start with current. So I know current is current density times A. Okay, and I'm going to say current, I'm going to make a couple substitutions here. For current density, I know current density, J, is related to the electric field and resistivity times A. And I'm going to make one more substitution. So if I call this the length of this wire L, length of the wire L, I could make another substitution for E, right? Remember, electric field equals your change in voltage over distance. Well, in a conductor, if we're talking about a conductor here, that electric field, and we're not looking at equilibrium here. So I know we said earlier in an earlier chapter that electric field is 0 inside a conductor. Well, that's going to be true if you're looking at electrostatic equilibrium. Right now, we're not looking at electrostatic equilibrium. Right, charges are moving in this wire, so electric field is not going to be 0. But instead, we're going to use that equation up there and plug in for E. Delta V, my change in voltage over length. So that's what I get if I plug in for E, and then resistivity times A. Okay, so we got this equation there. It looks kind of messy, right? Change in voltage, length on the bottom, resistivity on the denominator times area. So this usually gets grouped together. So we have I on the left equals delta V, and all this stuff here, A, L, rho, right? All that stuff is dependent upon the actual wire, right? So resistivity depends upon the material. Length is just the length of the wire, and A is your cross-sectional, I'm gonna say cross-sectional area of your wire. Okay, so this whole thing here, this whole thing depends on the actual wire. So rather than calling it two separate things, we're gonna bring this all, or combine all this into what we call resistance. Put that in a different color. So resistance equals rho L over A. And the unit for resistance, right? Resistivity is ohms. What was it? Resistivity, I said in the previous slide, was ohms meter squared, I think. No, ohm meter. And so the unit for resistance here is just ohms. Okay, so this equation becomes very important. So this is our resistance, and if I use that to plug into my original equation, I get I, current, equals change in voltage, or your voltage difference between the wire, over R. And this is a very well-known Ohm's law, so I'm going to drop that delta. Usually VB will be 0 or something like that. But it's a change in voltage over the wire equals current times resistance. So this is our macroscopic view. This is called Ohm's law here. Really important equation. We're going to use it over and over again. Let's see. Ohm's law. Put that. The equation for resistance doesn't have an equation. It's just a resistance of a wire in blue, what I box in blue. Okay, so Ohm's law pretty much gives us that relationship between voltage and current, right? We don't have to dive into the nitty-gritty of what is the electron number density. We don't have to look at electric field in the wire. It just tells us a direct relationship between voltage, and it is change in voltage. I kind of regret taking off that delta now. That change in voltage over that wire and relates that to current. Okay, so if you just look at that for a little bit, you can see if you have a large resistance, so let's say you had a battery. So you connect a battery to a wire, batteries keep the same voltage. If resistance goes up, let me put that up here. So if you have high resistance, right, if resistance goes up, right, you have high resistance, which means, remember where resistance ultimately comes from. You have a high resistivity, so a lot of collisions, right? That's what that goes back to. So a lot of collisions here. So you have a length, so those electrons are not only have a lot of resistance, but have to travel through a large wire or long wire, so even more opportunity for collisions. And area. So if area is small, or if it's narrow rather than large, you get a small amount of electrons, right? So all these things contribute to resistance. So if resistance go up, you have a lot more collisions. Those collisions are going to slow down your flow of electrons, right? Your current. So if resistance goes up, then our current is going to go down. All right, assuming voltage is constant, which most of the time will be if you connect it to a battery. Okay, so we're gonna be using Ohm's law quite a bit. We're gonna be using Ohm's law for the rest of this chapter. Ohm's law a lot in the next chapter. So really important law there. All right, so we are going to take a break from at this point, and then we'll start applying it to different problems.